Hey guys, so we are going to talk about section 1.7 today, which is all over linear and absolute value inequalities. I'm going to screen share with you the notes somewhat today, and then I'm also going to screen share some of the textbook today. I don't like to screen share the whole time if I can avoid it, because I want you to be able to see as much of the board as you can. Maybe if I can make it work, we might live it up. So before we talk about linear and absolute value inequalities and things like that today, we need to talk about a different way of notating this information. And so there's actually two different ways that well, there's three. There's the interval notation, there's set builder notation, and then there's using number lines or graphing. So those are the three ways that you're going to be asked to give information on linear and absolute value inequalities. So the first one that we're going to talk about is this interval notation, which is the top one on the notes. And it says this is a way to represent a range of solutions. And so we use parentheses or open circles, to represent less than or greater than. And we use these brackets, we use brackets or a closed circle to represent less than or equal to or greater than or equal to. This equal to part in the closed bracket or the closed circle means that we include that end point. We include that point in with the solution set. So that's the difference. Open circles mean, or parentheses mean, we don't include that point. We get really close as infinite possible. Whereas the closed ones mean we actually are going to include that given point. And in the notes, I reference a table on page 190 in your textbook because it does a really good job of showing you all this information. Let me see if I can move me over here. So there's actually two tables on page 190. There's this top table right here, this interval notation, and then it shows you what that means in a graph. But it also shows you right here, this set builder notation. So we have a closed interval, we have an infinite interval, and we have another infinite interval. So the closed interval, notice it has brackets. And so that means it's a set of real numbers between A and B that also includes the points A and B. It includes those endpoints. So on a graph, we would typically see it graphed like this. And that includes everything in between those 2 points, including the endpoints. Had this been parentheses instead of brackets, then that tells us that it would go really close to those endpoints, but it wouldn't include those endpoints. And so in set builder notation, we use curly brackets. Notice the curly brackets. And then we have this X with this vertical bar. That's standard procedure. That's always what it's going to look like. So it'll have this X with a vertical bar, and then you write your inequality right there. So bracket A comma B bracket is lying on this line. It includes every value between A and B, including A and B. So what that tells us is that we have X such that vertical bar means such that A is less than or equal to X, which is less than or equal to B. And that's exactly what this says. A is less than or equal to X because X lies somewhere in there or is equal to A. And then X is also less than or equal to B. Okay, we're going to do a lot of practice with this, and you'll get to see this method with the interval notation, the set builder notation, and the graph notation. We'll do all three of those with a lot of our problems today. The infinite interval says we start at A, or as close as we can get to A, and go all the way to positive infinity. So on a number line, I think going to the number line first is helpful so you can see the values. We start at A, and then we go on forever towards positive infinity. So if we go from that to set builder, it's X such that X is greater than A. X can't equal A because we have the open parenthesis, and X just has to be larger than A. So that's all you need there. It's a similar procedure for the negative infinite solution right there. But it's really this table 1.4, which I also include in the Canvas site under your notes for this week. I include this table because this one shows you every possible example that you're going to encounter. It has the interval from A to B where you don't include A or B. It has where you include both A and B, where you only include A, where you only include B, where you go from A to positive infinity. Like, it's just got every possible solution that you could have. It shows it to you in interval notation. It shows it to you then in set builder notation, and then it shows it to you on the graph. So this is a wonderful, wonderful tool to have at your disposal so that you understand how we're going to graph all of these. Okay? But even with all of that information, really the best way to get used to this is to do some examples. So let's do some examples. If you have my notes pulled up, then you'll have these examples right in front of you. And if not, then they're going to be right in front of you on there. I'm going to stop the screen share if I can remember how. Well, I don't remember how to stop screen share. Oh, it's over here. I've blocked it with myself. I will stop sharing my screen so that you can just see me and the board, and it'll be nice that way. So the first example that we're going to do says -1 to +4. Notice that the -1 is with a parenthesis. That means we're not going to include -1. We're just going to get really, really close to -1. So the instructions for this is to write, this is interval notation. We need to write it in set builder notation, and we need to graph it on the number line. No matter what order it tells you to do it in on your homework or your quizzes, I think going straight to the graph is most helpful, and then doing the other forms after that. So I'm going to graph first. So I have a standard number line right here, and it says my starting point is at -1. Now at -1, you can either put an open circle or you can just put the parenthesis. I'm going to put the parenthesis, and I'm going towards the right because that's my lowest point. So I'm going to put a parenthesis right there at -1. Then I'm going to go all the way up to +4, where I'm going to put a bracket. That means we are including the point +4 in our set. And then it's everything in between those 2 points. So this is graphically what our interval looks like. Now, how do we write that as a set builder? Well, set builder notation is always written in curly brackets, and then you have an X with a vertical bar. That says X such that. Okay, so X such that what? Well, what is the smallest value represented on our number line? It's -1. So I'm going to write that first. -1. -1 has to be less than X. It can't be equal to X because we have that parenthesis. So we get really, really close to X, but we're not actually equal to X, or not actually equal to -1. So -1 less than X, but then X has to be what? Well, it has to be less than or equal to 4 because we have that with the squared off bracket. And that's how you write parenthesis -1, 4 bracket as a set builder notation. You have X such that -1 is less than X, and X is less than or equal to +4, which is exactly what our interval looks like. And that's it. This is our interval notation. This is our set builder notation. And this is our graph, or our graphical notation. Let's try this other one, this one right here. We have 2.5, 4. Notice that we have a bracket and a bracket. So that means we're going to include both of those endpoints. My lowest endpoint is 2.5, so 2.5. So I'm going to come to my number line and go to 2.5. My largest point is +4. So I put a bracket and a bracket. And our solution set or our set is anything in between those two numbers. Now I'm going to do my set builder notation. So curly bracket, x such that, well, what's the smallest point? Smallest point is 2.5. So 2.5 has to be less than or equal to our x. We know that because it's a bracket, which has to be less than or equal to our 4, again, because of our bracket. Let's try one more. Move you down so you can still see that one too. Okay, this one says we have parentheses -4 all the way up to positive infinity. So the low end of our set is -4, but we're not including that because it's a parenthesis. And then it goes all the way to positive infinity. Well, positive infinity is never going to appear on our number line because infinity cannot be reached. You just get really, really close to it. I mean, it keeps getting further away. So the way we represent that typically is by putting a big arrow on our number line and then just shading it up until the big arrow. And that shows you that we start at -4 and we keep going on for forever. So how do we write this as a set builder? Well, start with our x such that, and then -4 has to be less than x. We know that because -4 is our smallest point. We don't include it because it's with the parenthesis. We don't need to put x is less than infinity because as long as x is greater than -4, we're fine because we can never actually get to infinity. So that's it. So that's how we graph on a number line. That's how we get our set builder notation. Now there's these two functions that we can talk about in terms of our notations and our solutions. One of them is called the intersection. So the intersection looks at two different groups, two different sets of solutions. We have set A and we have set B. And so A intersect B. This intersection sign is kind of like an upside down U. So A intersect B is the set, I'm trying to help you read math with words, is the set X such that X is an element of. This little weird E looking thing means element of. So X is an element of A and X is an element of B. So if you are in the intersection, then that means you are in both sets A and B, okay? So let me think about even a street intersection, because we talk about street intersections just in our everyday life. If you're on 4th and Broadway, if you stand right in the middle of the intersection, you're on both Broadway Street and 4th Street. That's what it means to be in the intersection. And the same thing is true with our sets. If you are in both A and B, then you are considered in the intersection. So I think the easiest visual way to represent this is with Venn diagrams. We have set A and we have set B, and notice they overlap a little bit. That overlapping area right here in the middle is the intersection. That is where A intersect B is. Because if you are in this intersection right here, you are in both sets A and set B. So only the values that lie right here are in the intersection. So that's what intersection means. There's another distinction called the union. This is A with a U, B, A union B. And that is the set of X such that X is an element of A, so X is in A, or X is an element of B. So to be in the intersection, it said X had to be an element of A and X had to be an element of B. But for union, you only have to be a member of one of the sets. So you don't have to be in both. You can be, but you don't have to be. You have to be either an A or B. And so to represent that on a Venn diagram, you have to be an A or you have to be in B. And this is A union B. So when you union two sets, you're taking two sets and you're clumping them both together to where we know that all the elements of A and all the elements of B are represented in the union. Think about when two people get married, their families are then fused together in the union and they're all together then. It's kind of the same thing with math when we talk about the sets. I think the Venn diagrams are the easiest way to kind of understand them visually. The difference between the intersection being here and the union being all of it. So notice the intersection is part of the union because if you're in the intersection, then you're in either A or B because you're in actually both of them. And so that's okay. So what do these look like on our graphs and with our different notations? Well, give you a problem. Sorry, I have to move some desks around to get you a good eyesight of this. Again, these are the exact same examples off of the homework or off of the notes. So if you have my notes digitally pulled up, I'm just going down the notes page. Okay, our example says to graph in order to find. In our first one, A, says we have 1, 4, intersect that with bracket 2 to 8. So I made two different number lines so that I can graph each of these on the number lines and then see where they intersect. Because that's the easiest way for me to do it. So 1, 4, my low end was 1, and my upper end was 4, and they're both with parentheses. So that set is represented like that on my number line. Bracket 2, 8 means I start at my low end of 2, and I go all the way up to 8. And I'm going to include the point 2, and I'm going to include the point 8. So this first one wants me to find this set intersecting with this set. So remember, to be in the intersection, you have to lie in both this set and this set. If you don't, then you're not part of the intersection. So the way that I usually do this is I look and I start with the furthest left. So the furthest left is here, is my top one starting at 1. Is the point 1 in both of these sets? No, it's actually not in either of them because it's in parentheses. So what is the smallest point that is in both sets? Well, if we keep moving along, point 2 is in the top set and point 2 is in the bottom set, because we have that bracket. So that tells me that 2 is my smallest point. And then I'm going to go all the way up to my largest point. Well, my largest point on the bottom is 8, but that's not my largest point on top. My largest point on top is 4, but 4 is not included, right? 4 is not included in the top, but it's included in the bottom. If it's included in one, but not the other, then you can't include it in the intersection because that point doesn't lie in set A. Set A doesn't have point 4. It has really close to point 4, even if point 4 is here. So you're going to write 4, but you're going to write with a parenthesis because 4 isn't in this set, but 4 is in this set. But we get really, really close to it. This is these two sets intersection. Now, what if, you can kind of see it over there, what if I'm unioning, that's a weird word, What if I'm combining these two sets using a union? Well, that's even easier than trying to find the intersection, because remember, union means you're taking all of set A and all of set B and you're smushing them together. And you're listing all of the elements. So all you have to do there is look at the smallest element out of both sets and the largest element. So, from a squeeze spot. So the smallest element was from set A. This first one was 1. It doesn't matter that 1 wasn't an element down here because you're unioning the two sets. So we have 1, and then we have all the way to 8. And 8 is included because 8 is included down there. That's all you do. So it's harder to find the intersection because you have to look at what overlaps versus the union. You just have to see what's the smallest element included in both sets and what's the largest element included in both sets. And me saying it that way maybe the smallest element out of the sets and the largest element out of the sets. Okay, let me screen share my notes with you. I'm gonna have to make it bigger and move this little box maybe. This is why I don't like screen sharing, because it moves things around. There we go. Okay, so there's all the information we've already talked about. There's the example I just did. And now there's this linear inequality right here. You solve the linear inequalities just like linear equations, except you have to flip the sign if you multiply or divide across the sign by a negative. And maybe that's confusing. I promise we will clear it up by working some examples. But if you can solve a linear equation, you should be able to solve a linear inequality, because the processes are exactly the same. There's just that one extra step of flipping the sign if you multiply or divide across by a negative. Okay, so let's do an example. We have 3 minus 2x is less than or equal to 11. So pretend like it says 3 minus 2x equals 11. We're going to solve it just the same way. We need to isolate our x. So if we're going to isolate our x, I'm going to subtract my 3 over. So that's negative 2x is less than or equal to, subtracting 3 over, I have 11 minus 3, gives me 8. If I need to isolate my x further, I would divide both sides by a negative 2. Now, this is where it comes in. I'm going to divide by negative 2, divide by negative 2, so I have x. This is the special rule. I divided by negative 2 across that sign, so I have to flip it. So instead of saying less than or equal to, it's now going to say greater than or equal to. I have to flip that sign. 8 divided by negative 2 is negative 4. So I have x is greater than or equal to negative 4. And that is the solution. Now you could be asked to give that as an interval notation. Interval notation, what is the smallest that our value of x can be? Well, x has to be greater than or equal to negative 4. So the smallest value that x can be is negative 4. And we include it with a bracket because it says less than or greater than or equal to. That equal to tells me it's a bracket. And then x is greater than that. Well, there's no end point for that. You can be all the way up to infinity. So we do infinity, parenthesis. You always use a parenthesis when you talk about infinity because you can never actually get to infinity. So we never actually include infinity in our sets. We just get really, really close. So there's our interval notation. If we needed to put that as a step builder notation, step builder is really nice because when you solve these linear inequalities, you already have your inequality right there written. So we just have to stick it in a step builder. So we do curly bracket x such that, that's always how we start our step builder, and then we put our inequality. X is greater than or equal to -4. That's all you have to do for step builder, which is super nice. If you had to graph this, we've already done this. Actually, I think we've already done this exact one, but I'll show you again. You have your number line. And then I always go off of my interval notation because I think it's easiest to see. We're going to put a bracket at -4, and that opens to the right, just like in our notation. We put a big arrow on our right-hand side because we're going to infinity. And we shade in everything in there. So for these assignments, you could be asked to give just the inequality, like just the answer. You could be asked to give the interval notation. You could be asked to give the step builder notation, or you could be asked to give that information graphically. And some of the problems will actually have you do it all of these ways. So you have to be able to go back and forth between all of these different methods. All right, let's do another one. I'm just going to erase this one. Remember, if you need more time to look at stuff or write down stuff, you can always pause the video. All right, this one says -2x minus 4 is greater than x plus 5. Again, solve it just like a linear equation. I want to get all my x's on one side and all my numbers on the other. So I'm going to subtract my x over and add my 4 over. So if I subtract my x over, I get -3x. If I add my 4 over, then I get 9. I'm going to divide both sides by -3. So x, I'm dividing by a negative, so I have to flip my sign. So instead of saying greater than, I have to say less than. 9 divided by -3 is -3. Let's do step builder first this time. Step builder says curly bracket x such that, and then I simply put in my inequality. X is less than -3. So if x is less than -3, do I have a low point or a high point? Like, is -3 the highest my x is ever going to be, or is that my lowest that x is ever going to be? Well, if x has to be less than -3, then -3 is actually my high end. And since it's not equal to, I'm going to have a parenthesis. What is the lowest my x can be? Well, it can go all the way down to -infinity. Because x just simply has to be less than this -3. So that is my interval notation. If I was going to graph it, -5, -4, -3, -2, -1, 0. The highest my x can be is -3 with a parenthesis. The lowest it can be is -infinity. So I do a big arrow and I shade in the inside from there. All right. Let's do one last one. This is the most complicated that you will face. And the only reason why I say it's complicated is because it has fractions, and I know you all love fractions. So we have x plus 3 over 4 is greater than or equal to x minus 2 over 3 plus 1 over 4. So if you have one like this where it's got a bunch of fractions in it, and you don't like to deal with fractions because none of us do, then the first thing you're going to do is you're going to multiply everything by the least common multiple, or the least common denominator. Meaning, if I write out over here, I write out my factors or my multiples of 3 at 3, 6, 9, 12, 15, and so on. And I write out my multiples of 4, 4, 8, 12, 16, dot, dot. I want to find the smallest number that both of my denominators, because I had 4 and 3 as my denominators, find the smallest one they have in common. Well, they both have 12 in common. That means I'm going to multiply everything by 12. Okay, I'm going to multiply every single thing by 12. So I have 12 times x plus 3 over 4 is greater than or equal to 12 times x minus 2 over 3 plus 12 over 4. Now you may be asking yourself, why would we do that? Because we still have fractions, but only for a minute, because it's going to reduce. Notice we have 12 over 4. What's 12 divided by 4? It's 3. So we have 3 times x plus 3 is greater than or equal to. Over here we have 12 over 3. What's 12 divided by 3? 4. So we have 4 times x minus 2 plus, and then the last one we just have 12 over 4, which is 3. So by multiplying by something that both of our denominators have in common as a multiple, we're able to eliminate the denominators entirely and then just work it like a normal equation or inequality. I'm going to distribute my 3 in. I'm going to distribute my 4 in. So I have 3x plus 9 is greater than or equal to 4x. And then I have a minus 8 plus 3, which is a minus 5. So I need to get my x's on one side and my numbers on the other. Just to save me having to flip-flop, I'm going to move my 3x over and I'm going to move my 5 over. That way I keep my x's positive and I don't have to think about flipping my sign. So if I add 5 to both sides, I have 14 is greater than or equal to, and I subtract my 3x over x. So 14 is greater than or equal to x. If you like your variable to be first, you can say x is less than or equal to 14. That is fine. It's the exact same thing. So if x is less than or equal to 14, that tells me that 14 is my upper limit. So 14 is my upper limit, and we include it because it says is greater or is less than or equal to, and it goes all the way down to negative infinity. Step builder would be x such that x is less than or equal to 14. You might be asking, well, what if I didn't switch it over here? What if I left it as 14 is greater than or equal to x? Could I put that in here instead? Yes, you can. It does not matter either way. Both are correct. Okay, so that's how we solve linear inequalities. If we scroll down in our notes, you see the examples that I've been doing and I've been graphing for you. Right there's the one we just finished. And so right here, we have compound inequalities. Okay, compound inequalities means we're going to split our inequality into 2 inequalities, or you can think about it as doing all 3, like, you know, when we do, we move stuff over, like I subtracted I added my 5 over, I added 5 to both sides. With compound inequalities, you don't just have 2 sides, you're going to have 3 sides. So you can think about it as doing the same thing in all 3 sections, or we can split them. And if that doesn't make any sense, don't fret. I'm going to do the next example both ways so that you can decide which way works best for you. Both ways are mathematically fine. I have no problem with you choosing one way over the other. For the most part, as we move throughout the semester, I will use the three-sided method instead of the splitting method. But that's just my personal preference. You don't have to do it my way, you just have to do it correct, okay? So what does a compound inequality look like? Well, we have -3 is less than 2x plus 1 is less than or equal to 3. This is a compound inequality. Notice we have 3 different sections. We have 2 different inequality symbols, and that's what that means. That's what a compound inequality is. So this, if you are going to split it, then what we're doing is we're looking and saying, okay, -3 is less than 2x plus 1. Okay, so I'm going to write just that part. -3 is less than 2x plus 1. And that's its own inequality, and I'm going to leave it just like that. However, if I keep reading, it says 2x plus 1 is less than or equal to 3. So this part is another inequality. 2x plus 1 is less than or equal to 3. So if you were doing the split method, that's how you're going to do it. You're going to split it up into 2 separate inequalities and you solve them by themselves. So I have -3 is less than 2x plus 1. I need to isolate my x, so I'm going to subtract my 1 over. I'm going to divide both sides by 2. So I get -2 is less than x. Now I'm going to come over here to my purple equation, and I have to solve for x. Again, I'm going to subtract my 1 over. Going to divide both sides by 2. And I get x is less than or equal to 1. Okay, so how do I put these together? Well, -2 is less than x, and x is less than or equal to -1. So -2 is the smallest x can be, but we're not including it. And x can go all the way up to +1 and include it. So that would be our step builder, or excuse me, our interval. Our step builder would be x such that, we'll start with your low end, -2 is less than x, but x is less than or equal to 1. And that's how you combine those back together to make this one inequality to put inside of our step builder. I'm not going to graph it because I think you can understand how to graph it. So this is the split method, okay? There's nothing wrong with the split method. The reason why I don't prefer the split method is because sometimes combining them back together there at the end to find your actual set can be confusing. And so I don't love doing that. So here is the three-sided method. I'm going to scoot you down just a tiny bit so you can see this three-sided method as well. Same exact problem, -3 is less than 2x plus 1 is less than or equal to 3. Okay, this is our compound inequality. Now, if I'm trying to get x by itself, x is in the middle. So how do I get x by itself? Well, how did I get x by itself over here? I had to subtract 1 to get that away from it. That's what I'm going to do here. But instead of only doing it on 2 sides, I have 3 sides. So I have to subtract 1 from here, I have to subtract 1 from here, I have to subtract 1 from here. That's what it means to do the same process in all 3 sections. So I have -4 is less than 2x is less than or equal to 2. I'm still trying to get x by itself, so I'm going to divide every section by 2. And I get -2 is less than x is less than or equal to 1. Notice this is the same inequality that we have right here. Exact same inequality. And I think this is a lot less work because you did the exact same steps, both times when you split it. So this time we didn't have to split it and we just keep going and doing the same work. We're going to get the same interval notation. We're going to get the same set builder notation because we have the same inequality. So when you're doing compound inequalities, you can split or you can do the three-sided method. Like I said, I will always probably do this three-sided method because it's less work in my opinion. So I know I said I wasn't going to screen share the whole time, but it seems to be working out okay. So let's talk about, let me see if I can do this. I'll just move me right over the stuff. There we go. So solving absolute value inequalities. So remember, absolute values tell you the distance away from zero. So this is going to be a little confusing in the math speak, but then we'll do some examples and hopefully it'll make a little bit more sense there. Okay, so if you are solving an absolute value inequality, we say if U is an algebraic expression and C is a positive number, the solutions to the absolute value of U is less than C are the numbers that satisfy negative C is less than U, which is less than C. If we have the absolute value of U is greater than C, then the solutions are the numbers that satisfy U is less than negative C or U is greater than C. I know that that's a lot of math speak. You want to probably write it down. It's good notes to have, but I think seeing some examples makes that make a lot more sense. So we have the absolute value of x minus 4 is less than 3. Okay, so which situation do we have? Do we have the first situation or the second situation? Well, let's look. We have this expression is less than a positive number. So less than a positive number, we're talking about number 1, solutions where U is the absolute value of U is less than C, means that we can say negative C is less than U, which is less than C. That's how we drop our absolute value signs in order to solve this. So instead of leaving it written like this, I'm going to write negative 3 is less than x minus 4, which is less than 3. Had our problem originally said less than or equal to, then I would have less than or equal to as both of my signs here. But since it was just less than, I'm leaving it just as that. Now we have our compound inequality that we just solved where we can do the three-sided method. So this is x minus 4, so I'm going to add 4 to all three sides. So I have 1 is less than x is less than 7. So my set builder is x such that 1 is less than x is less than 7. And from there, I can do my interval notation. 1 would be my smallest, but it's not included. And I go all the way up to 7, but also don't include that. If you like graphs or pictures, I did graph this one in the notes. You can see right here. If you know that, the absolute value of x minus 4 looks like this. And then it shows you the interval on which the y values are. So let's do, I'm going to leave up the general notes and I'll write up another example. We have negative 2, absolute value of 3x plus 5, absolute value plus 7 is greater than or equal to negative 13. Okay, we don't have just the absolute value of U in comparison to our C yet, because we have this +7 and we have this -2. So we have to do some simplifying before we can compare to know if we are in if we're going to be dealing with a number 1 situation or a number 2 situation. So the first thing I'm going to do is subtract the 7 over, and I'm rewriting everything else the same. So subtract the 7 over, I have a -20. Now I'm going to divide both sides by this -2. But when I divide by a negative, it flips my sign. -20 divided by -2 is 10, and it went from a greater than or equal to a less than or equal to. Now I have an absolute value less than or equal to a positive number. So which situation is that? Well, it's the same situation as the one we just did. It's situation number 1. That means I can write this as -10 less than or equal to 3x plus 5 less than or equal to 10, and I can solve it just like normal. I'm going to subtract 5 from all of my sides. I'm going to divide all of my sides by 3. Notice we get a 5/3 on the right. That's okay. You can have fractions. Don't be scared of fractions. So step builder, x such that -5 is less than or equal to x, which is less than or equal to 5/3. Since both of our signs are less than or equal to, we know we're going to have bracket, bracket. Low point is -5. My high point is 5/3. There's my step builder. There's my interval notation. All right, let's do one more example, because obviously we've done 2 examples that are situation number 1 with our absolute value. So I bet you can guess what the next one's going to do. It's going to be a situation number 2 type of problem. We have 7 is less than absolute value of 5 minus 2x. So we have, if you want to rewrite it because you don't like how it looks, we have absolute value of 5 minus 2x is greater than 7, if you want it to be like that. Then it looks exactly like our step number 2 or our situation number 2, where we have the absolute value of u is greater than c. So if that's the case, then what do we have to do? Well, if that's the case, then we have u is less than -c, or we have u is greater than +c. So we're going to have to split in this one. So we're going to have our inside less than a -c, or we have our inside, the 5 minus 2x, is greater than our +c. Those are the 2 situations that we can have, and we have to solve them separately. So I'm going to subtract 5 and divide both sides by that -2, which flip-flops my sign, and I get x is greater than 6. Or over here, I'm going to subtract my 5, 2, divide both sides by -2, which flips my sign and tells me x is less than -1. So I want to show you this on the graph, just because we haven't really had one that does this. 2, 1, 0, 1, 2, 3, 4, 5, 6, 7. Okay. So we had x is greater than 6. So that means we have an open parenthesis, and x is going on for infinity, like that. This says that x is 6, infinity. Or we have that x is less than -1. Well, -1 is this way, and it's going to -infinity. So we have -1, negative infinity comma, -1. So on a graph, that's what they're going to look like. But we can be in either this one or this one. That means that our solution is, oops, let's write the smaller one first. Let's write the purple one first. -infinity, comma, -1, union 6 infinity. Because our answer could be over here, or our answer could be over here. And since we have that or, that was the big word in there, that tells me that we are using a union. So that's how you would write it as an interval notation. Step builder notation isn't hard. X such that X is less than -1 or X is greater than 6. You can use words in your step builder, so that word or there is okay. It just tells you that it lies either on this extreme, right here in this part, or it lies over here. And since they don't have anything in common, we can't use an intersection or any other form to differentiate that and combine them together. So that is the end of 1.7 over linear and absolute value inequalities. Good luck on your homework.